Hey again, welcome to another video. In this video, we are going to talk about something called power functions. I'll tell you what that means in a minute, but I want to tell you why we're learning it. We are learning about power functions for one reason: to get a picture of the end behavior of a polynomial. Here's what's going to happen. When you have a polynomial and you have found your leading term, the end behavior of your polynomial is going to follow that leading term. And that leading term is a power function. So what a power function means, it's just a polynomial with one term. So the whole concept of what we're going to be doing, remember I always teach you where we're going. The whole concept of what we're doing is look at your polynomial, look at your leading term, find the degree, check out the leading coefficient. That's a single term you're looking at. That power function, one term, is going to tell you the end behavior of your polynomial. So that's why we're talking about power functions, is to get a picture of your end behavior. So that's why that's what I want you to be thinking of. Is the polynomial going to be looking like this, like this, like this, or like this at the end of it, at the ends? Because that's the only four cases that you can possibly have for polynomials. So we're going to talk about that, but that's the concept. So with that in mind, thinking about that, let's go through and talk about power functions. So what a power function is, it's just this polynomial with a single term. Like I said, we're going to be looking at the leading term as our power function. So what that means is that they're pretty easy to graph and they're very, very predictable. So in order to get a kind of a view of what power functions do and what they look like, let's look at a few very simple power functions. From here, we're going to draw some conclusions about what if your n is even, what if your n is odd, because they're all going to be this way. We'll talk about just a picture in our head of what these four would look like, and then how to go and use transformations, which you've already done. I'm not going to spend a whole lot of time on that one. So our power functions are very predictable, and they follow one of two patterns. Whether they are even or whether they are odd, they're going to follow one of those two patterns. An even function is symmetrical about the y-axis, and an odd function is symmetrical about the origin. And that's the only two things we can possibly have with a power function. So, and why? Why? Because if we have anything else, there'd be something added or subtracted to it or within it to shift it around. And doing that would create more terms. Even if I had parentheses here with something inside, I could distribute, right? And that would give me more terms. So because power functions have only one term, there's no shifting. There's no way to not be symmetrical about either the origin or the y-axis. I had those backwards, by the way. The origin of the y-axis if you have power functions. So very nice, very predictable. Let's take a look at it. What we're going to do here is just plug in -1, 0, and 1 and get a pattern. We're going to take the pattern and talk about even and odd power functions. So if I take f of x equals x and I plug in -1, I'm going to get -1. 0, I'm going to get 0, and 1, I'm going to get 1. So we'd have this nice function that would have those 3 points. Now let's go over to x squared. Now I'm going to draw the curves in just a minute because I want you to follow the pattern. Let's go over to x squared. I'm going to plug in -1 and get +1. 0, get 0, 1, and get 1. So I have these 3 points. And again, we're going to draw the curve in just a bit. Let's go down to x cubed. If I take x to the third power and I plug in -1, 0, and 1, -1 to the third power is -1 again. 0, I'm going to get 0. 1, I'm going to get +1. We get exactly the same points as f of x equals x. The exact same, what we call key points. Key points, if you remember from lots of videos ago, are a great way to graph with transformations because it lets you move the graph around and still have 3 points to graph with as long as you understand the shape. These are the same. And in fact, when we get to odds, every odd function, power function ever is going to have these 3 key points. -1, -1, 0, 0, and 1, 1. Every single one of them will have those 3 key points. Now let's look at x to the fourth. X to the fourth power, if I plug in -1, if I evaluate that, -1 to the fourth power is +1. 0 gives you 0. And 1 gives you 1. These are the exact same 3 points we got in x squared. And in fact, every even power function ever is going to have those same 3 key points. -1, +1, 0, 0, and 1, 1. So really, all that differentiates between our odd and our even is this side of your graph. This is what dictates whether you're going to be symmetrical about the origin, be able to rotate that 180 degrees, or about the y-axis, be able to fold it over and have a mirror image. It's just that exponent. So if we had, and this is where the phrase even or odd really comes from, it's from power functions. If we have an odd exponent, you are going to have an odd type of symmetry about the origin. If you have an even exponent and your power function, you're going to have even symmetry about the y-axis. That's true all the time for power functions. So wait a minute. If we always get the same 3 points and all of them go through the origins, you notice that? They have to, because they can't be shifted around. There's no adding, there's no subtracting, there's no other terms, just one. They all go through the origin. They all have the point 1, 1. Odds have -1, -1. Evens have -1, +1. And that dictates your symmetry. They're very predictable. So what is the difference between these two graphs and these two graphs? The difference is the radicalness of your graph itself. And here's what I'm going to say. As your exponent gets higher, these graphs get more dynamic, more dramatic. So f of x equals x to the first power, man, that's just a straight line. That's a constant slope. Do you remember that the slope here would be 1? Up 1 over 1, up 1 over 1, up 1 over every time. That's a constant slope. So that's just our normal diagonal straight line that we create a 45-degree angle between x-axis and the line itself. That's it. But as we start increasing our exponent, we start curving it. So we start going, and then x to the 5th would be even more dramatic, and x to the 7th even more dramatic, to the point where it would look almost like a box, like this sort of boxy in nature. So x to the 3rd is going to be a lot more curved in its nature. If we had x to the 5th, maybe I can superimpose that here real quick for you. X to the 5th would still go through the same 3 points, but the way it would do it is much more dramatic. So very steep and then super shallow and then very steep again. And the higher our exponent, the more dramatic our graph is going to get. So that's why I put this odd over here. I'm not going to put any graph on here at all, because if you have an odd exponent, it's either 1 or 3 or 5 or 7 or 9 or so forth, all of them are going to climb. Every single one of them is going to climb. Every single one of those is going to climb from -infinity on the y-axis to +infinity. They're all going to look like this. Now, if we have a coefficient that's negative, yes, we can switch them, but they're all going to look like that. Every single odd ever is going to look like that. That's kind of cool. That's kind of predictable. We have some key points there that we can use in our graph. The idea is, hey, if you know that your leading term, remember, we're always going to leading term, we're always going to graphing here. If our leading term is an odd degree, we know that the end behavior of our graph is going to look like that. That's super cool. We also know that if it's like a 5th power, it's going to be very dramatic. 7th power, very dramatic. 3rd power, not so much. 1st power, well, we kind of know how to graph those already. So that would just be a straight diagonal line. That's kind of easy. But they're all going to have those key points. Now, as far as evens, sort of the same thing happens. We know that x to the 2nd power has this really nice normal parabola. We're very used to it. X to the 4th is going to start getting more dynamic, more dramatic. It's going to be a little flatter here and steeper as we get past 1 and -1. So what happens with our degree, remember degree is the largest power we talked about in the last video. What happens with our degree is that within 1 to -1, we're very, very flat. And the higher the degree, the flatter we are. Outside of 1 to 1, we're very, very steep. And the larger the exponent, the steeper that we are. Do you notice that? The x to the 5th would be very steep until we get here, and then it flattens out. Flat, 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 flat. Very, very dynamic curve. and then outside of that, very, very steep. Very interesting. The same thing happens with x to the fourth. If we would have something like x to the sixth, x to the eighth, it almost start looking like most of a rectangle would be almost straight down, very, very sharp curve, almost flat, very, very sharp curve. And so the higher exponent we get, the more dynamic. But all of our evens are going to fit this model where we go through -1, 1, 0, 0, and 1, 1. They're all going to look like this. Yes, if we had a negative coefficient, it would reflect it. Do you remember that? How a negative coefficient reflects a graph? We can do that, but this is the main point of our power functions. I want to go through it just one time to make sure you get the main point. The main point is when we get to graphing polynomials, which we're almost there, we're going to look at the leading term. The leading term is one term. Therefore, it's a power function. It will either be even or odd. It will either have an even degree or an odd degree, and that will tell you whether your function does this or does this. If it has a negative in front of it, well, it can reflect it. Then this or that. That's it. We can also start graphing this with our key points, which is pretty cool. We can use that for transformations mostly. But let's imagine something for a second. Let's imagine that these are our leading terms of 4 different polynomial-driven functions. And let's see if we can put a picture to it. So here's what I want you to do. If these are our leading terms, I want you to think about f of x equals 2x and think in your head whether that is an even or an odd power function first. Remember that even or oddness of functions has absolutely nothing to do with the coefficient, has only to do with the exponent. So the exponent here is 1. And you go, wow, that's an odd power function. How is it going to look? Is it going to look like this? Is it going to look like this? In just the generalness. Well, this is a odd. So it's going to have to go through -1, 1, 0, 0, and 1, 1. It's going to have to climb. So it's going to have to climb from -infinity to +infinity. We'll talk about domain and range here after we cover this. So here in our case, that is going to be this sort of climbing function. And now we think about it. What's the exponent? So our exponent's 1. It's not very dynamic. In fact, it's going to be a straight line. So we picture that in our head. This end behavior looks like this. Same slope, slope of 2/1 throughout. It's just a straight line. It's going to go from -infinity to +infinity on the y-axis. That's pretty cool. How about the next one? The next one is -3x to the second power. First thing we want to do, understand that this should be the leading term of some larger polynomial. We're just finding end behavior, how it looks at the tails. That's what we want. Well, that has what type of an exponent? Well, it's a 2. That's an even. Even functions have to look like this or this, depending on the coefficient. So we know that if I covered that -3, it would go through -1, 1, 0, 0, and 1, 1. So this is this almost parabola, that is a parabola, this almost parabola type of even. And now we look at our coefficients. Well, that's a negative. What do negatives do? What's the 3 do? Remember there's some transformations. If you need to watch that video, go back and watch transformations from a while back, because that will tell you that, hey, that negative, that reflects it. That 3 makes it narrower, but it doesn't take away the fact that that's an even, and that means symmetry about the y. So this is even, yes. Reflected, okay, and more narrow. That's telling you end behavior. So if this was a larger polynomial, and this was the leading term, the term with the highest degree, or term with the highest exponent, giving you a degree of 2, that this would have an end behavior that is downward, even, and narrow. That's what that would tell you. How about this -x to the third? So we think, let's see, -x to the third, if that's going to be our leading term, that's a power function. It's got a degree of 3. So 3 is odd. 3 has this idea of -1, 1, 0, 0, 1, 1. Okay, it's climbing. How is it? Let's cover that up. That would be climbing. How is it climbing? Well, it's got this sort of curve in it. It's not straight. It does have a curve in it because of that power 3. Now think about the negative. That negative would take here's my odd, and now I'm going to reflect it. So this power function says I'm going to be dropping. So this curve downward. And that's, if this was a leading term of some larger polynomial, we would understand the end behavior of that saying, yep, I'm going to look about like that. It's a power 3, so it's going to have this curve in it. Yeah, a little bit more dynamic than just a straight line. It's negative. That means it's reflected from this. So we're dropping from positive infinity to negative infinity. Last one, how about x to the fourth? If it's 7x to the fourth, can you picture it? Can you picture that this is symmetrical about the y-axis? Just like this was symmetrical about the origin. It was, okay, we could reflect it still symmetrical. This is symmetrical about the y-axis, so it has to match up on both sides of the y-axis. This is a positive 7, so this is even, looks like this. Positive 7, okay, it's not reflected. And 7 itself says, I'm pretty narrow. So the end behavior of this graph, wherever it comes from, looks really narrow like that. It's going to be very dynamic. I hope that makes sense. I hope you can see here the value in understanding what our power functions are, because they're going to be coming from our leading terms. Our leading terms are going to give us this end behavior, and that's really, really nice to know. As far as our domain, because these come from polynomials, and polynomials have a domain of all real numbers, the domain for all of these is all real numbers. There's not a number that you won't be able to plug in and get something out, get a real number out. So all of them are real numbers. There are no negative exponents, there's no rational exponents, there's no logarithms. Therefore, with these polynomials, you can have all real numbers all the time. Now, as far as our range goes, we've already talked about key points, we know that. As far as our range, the range for an odd power function, look at it. Every one of these graphs, even if it had been negative and reflected, it would go from negative infinity to positive infinity on the y-axis. So every one of them is climbing from all the way down there to all the way up there. So our range is negative infinity to infinity on the y-axis. This is not true for evens. Range for evens is from 0 to positive infinity or 0 to negative infinity, depending on whether you have a negative in front of that power function or not. And the way we'd write that, 0 to positive infinity or negative infinity to 0, signifying the upper half of the y-axis and the bottom half of the y-axis. This is if you have a positive power function, so no negative in front, then we'd go, well, obviously upward. That'd be 0 to infinity. Or if you had a negative in front and reflected it, we'd go from negative infinity up to 0. These always have to be written in order. So I hope that makes sense to you. I hope that you understand the idea of we're taking leading term and we're just seeing whether it's like this, like that, so odd, positive, odd, negative, or this or that, even with a positive, even with a negative. That's pretty much it. One thing that I said it, I didn't write it down. I just want to make sure that you understand that odd power functions are symmetric about the origin. I always said that, but make sure we write a little note there. Symmetric about origin, so we have there this idea of rotate 180 degrees, you get the same picture. And then symmetric about the y-axis. We've talked about it, but that's about it. So we have key points. We know that all odd power functions ever go through -1, 0, 0, and 1, 1. That gives us a climbing graph for positive or a falling graph if you reflect it. Even ever goes through -1, 1, 0, 0, and 1, 1. That gives us a climbing graph that's symmetric about the y. If we have a positive in front of our power function, or reflect it, we have this falling graph, or downward opening, so it's a better way to say it, if we have an even with a negative in front of it. We have our range. Hey, that's all real numbers for our domain for both of these. All real numbers for our range for odds, not all real numbers for evens. You're either going to choose the upper half or lower half of your y-axis, depending on whether you have a negative in front of your power function or not. And then we have two different symmetries, about the origin or this mirror image about the y-axis. Now, let's go on. Let's talk about graphing these with transformations. We've done this very quickly before. I've taught you this before. We're going to do this very quickly right now, just to make sure that you see it one last time, that this is uses some ideas of symmetry, but because we're shifting it, you're gonna lose the idea of being an odd or an even function. We're still gonna use the fact that it's based on it, but it's not gonna be an even or odd function any longer because we've shifted away from the y-axis and away from the origin. We still use some ideas though. So let's identify it with g of x. Firstly, what's it based on? Is it based on an even power function or an odd power function? And of course, we're gonna look at the exponent and go, that's an odd power function. Now, honestly, are you really going to want to distribute that and graph this as a polynomial? Because it is a polynomial, but graphing that would say you don't just get to distribute the 5. You can't do that. You could find your leading term that way, but you don't just get to say, hey, x to the 5th plus 32. No. You take x plus 2 times x plus 2 times x plus 2 5 times, distribute that, then distribute the 3, and then subtract the constant of 3. And then you'd have a polynomial. That's crazy. If we have something that's nicely factored, man, what we can do is we can transform this. We can use our transformations. We should understand that that is a shift down 3, left 2, and that 3 impacts our key points. So this is why we needed to know about the odd power function that this is based on, because this is going to give us key points. So let's go through it. If we shift down 3 and left 2, that's a horrible left 2. We have this idea of a new origin. That's where the new origin would be. If we take our key points and pretend that that is the origin, then we can use the sort of, this was based on an x to the 5th power function, to graph from that point. I've done this in transformations, just kind of refresh your memory. If our key points are -1, 1, 0, 0, and 1, 1, why do we know it? Because that's an odd. That odd says every power function with an odd degree is going to look like this. It's going to have -1, 1, 0, 0, 1, 1. We're just shifting it. So we said, yeah, we're down 3, we're left 2. What this does, this says, hey, take your 3, multiply your outputs, not your inputs. 1 times 3 is 3. 0 times 3 is 0. 1 times 3 is 3. And if we graph these key points from our new sort of xy axis, from our shifted xy axis, we're going to get a power function that's been shifted. So we're taking two ideas. We're taking the idea of transformations, we're taking the idea of power functions, and we're combining them. We're saying this is a shift down 3, that's a shift left 2, this is a multiplication of an output times 3, we've talked about it before, and that power 5 says you have an odd here. Odds are -1, 1, 0, 0, and 1, 1. Put the ideas together. Let your shifting take you down 3 and left 2. Let your power function say, here's my key points. Let your multiplication of your output say, here's my new key points, and then plot them. If we plot, let's see, -1, I'm sorry, I messed up, and you should have caught it, hopefully. I had my key point wrong. So my key point should be -1, -1, 0, 0, 1, 1. That's -1. 3 times -1 is -3, 0, 0. So that's where I got messed up. Good thing I checked my work out as I was going. 0, 0, 1. Here's 1, 1, 2, 3, right there. And if we go a little bit lower, 1, 2, 3, I'm kind of estimating here. We'd have a key point of, from our origin, -1, -3, 0, 0, and 1, 3 from our new origin. We're combining these ideas. This is where our power function would be based on after we shifted. We're going to get a very dynamic climbing graph. And we know it's dynamic because that power 5. So we're using two ideas. We're using shifting to get down 3, left 3, and then power function to get key points, multiply them. So let's take a look at it. If we know it's a super dynamic graph and we're going through these points, we're going to make sure that we go up, make it crazy dynamic. Remember, these are sketches here. And we have a very good picture of that graph with very, very minimal work. That's the way we can use transformations, down 3, left 2, the idea of key points from our power function, -1, -1, 0, 0, and 1, 1. The idea of multiplying, that's another transformation idea. And then shifting and getting the look of a power 5 power function where a sort of new xy axis is. Are these dotted lines actually here? No. It's a graphic organizer to give us a very good picture of what we're doing. It's allowing us to take a look of a power function, which is always at the origin, and give ourselves sort of a new origin to graph it from. It's not really new origin, but it works really, really well. Let's try the last one. So one issue that we have is that polynomials are always in order, and we really do want our transformations in order too. So with that being in order, let's take a look at it. First thing that I want popping into your head is what type of a power function this is based on. So we just look at the exponent and go, that's a power 4. So how do power 4s look? Well, they're symmetrical some way, either upward or downward, but they're symmetrical. They also have some key points. Key points for these even power functions are -1, +1, kind of messed it up before, 0, 0, and 1, 1. So those are our key points. What we're going to do is allow our transformations, our shiftings, to move our origin, to adjust our key points, and let us graph a power function at sort of a new origin. It's not really there, but allows us to use these ideas in conjunction with one another. So we sort of have a feel for how this is going to look, at least the symmetry about some sort of an axis of symmetry. We know our shift says we're going to be going up 3. We're going to be going right 2. And that creates this new origin, this new x and y axis where we can graph a power function from. Is it really going to be symmetric about the origin or about the y-axis? No, it's going to be symmetric about your new origin or your new y-axis. That's the point of why I'm having you do this. We're sort of cheating at it. We're using, while we're thinking about it, being smart about it, and using 2 different techniques. Now, let's go ahead and do it. Because our key points are -1, +1, 0, 0, and 1, 1, and because we have this -1 that's being multiplied by our outputs, it will affect our outputs. It will reflect them. So this would give us -1, -1, 0, 0, and +1, -1. And if we graph those in relation to our new x-axis, 0, 0 is our new sort of origin. -1, -1, right about there. +1, -1, right about there. And then we understand this is a degree 4. That's very powerful. That's very dramatic. And we know that it's symmetric about our new y-axis, this axis of symmetry, and it's downward opening. We expected it to be downward open because of that negative. So let's go ahead and do that. It's not a parabola. It sort of looks like one, but it's more boxy. It's much more dynamic, very much sharper curves in this thing. One thing I do want to say is these are sketches. If you have to be more accurate, you do things like, hey, plug in 0 to find your y-intercept. So take and plug in 0 here and figure out what your y-intercept would be. Plug in 0 here, figure out what your y-intercept would be, the actual y-intercept that you would have. Set this equal to 0 and find x-intercepts. Sometimes it's not that easy. And oftentimes they're not whole numbers. So if you had to do that, you could. Also, one thing that a lot of people do is they'll plug in a number outside of this range somewhere, outside of this, this interval somewhere. They plug in something like 5 or 4, plug in something like -1 to get additional points. However, I gotta warn you that with these exponents like 4, 5, 6, they are just super up there, super down there. They get so dynamic, so fast, that they're almost ungraphable for things outside of where like your vertex would be, or your point of symmetry. In this case, here and here. When we start getting way outside of that, these exponents make values that are just huge or really, really, really negative. And so they're very hard to graph. So a little recap to make sure we got this. Power functions are one term. What we're going to be doing is looking at a leading term and saying, hey, this is going to model the end behavior for us. There's really only 4 of them. Because your polynomials always have a domain of all real numbers, you never have any issues with it, you can only have 4 looks. And they're all going to be continuous. They're all going to be smooth, nice curves, but they'll only look like this. Odd, negative odd, even, negative even. That's it. All we have to do is be able to understand what our function is based on, odd or even in this case, maybe understand some shifting, down 3, left 2, take that as an output multiplication, that's a factor for your output. Here, up 3, right 2, factor for your output, multiply it and use your key points. When we get to actual polynomials where we're graphing with multiplicity and things like that, we'll be there very, very shortly. Our end behavior just says where we're pointed, this or this, and that's pretty much it. So I hope that makes sense. If you're a little bit sloppy on the transformations, maybe go back and check that video out about what the down 3 and the up 3 came from, the left 2 and the right 2, because that might be confusing for you, and how we take this number to multiply our outputs of our key points. So if you forgot that, maybe check it out. Other than that, I hope you saw what we did. We just took the idea of a power function and the idea of transformations, and we just married them together. That way we can use the ideas of a power function. Hey, there's symmetry. We're just moving the place of symmetry by transformations. Hey, there's key points. We're just moving where the key points are by transformations. And it's pretty cool. Odds are symmetric about the origin, evens are symmetric about the y-axis. So if we move those things, we still have that sort of symmetry, just somewhere else. So I hope it makes sense. I hope that you are still with me. And next time we'll talk about getting into zeros of polynomials and getting into multiplicity. Have a great day.